Hi, I am Milioto, and I will be presenting our approach for semantic segmentation of crops and weeds in precision agriculture, which leverages background knowledge for convolutional neural networks. Our approach allows for accurate real-time semantic segmentation of crops, weeds, and background, exploiting expert knowledge in combination with deep learning. This allows us to use a purely visual classifier without exploiting crop row geometry or hard-to-obtain visual cues such as near-infrared information. Novel perception control weeding systems, such as the one mounted on the robot on screen, can perform weeding on a per-plant basis. For this, the system needs to be able to accurately distinguish between weeds and crops, allowing the robot to effectively treat the field, minimizing the amount of herbicides and not damaging the value crops. Most approaches to this task require a pre-segmentation of the images into soil and vegetation areas in order to generalize well to new conditions. This requires a readaptation effort for hyperparameter tuning in each field, given the variance of the conditions such as different soil types, growth stages, and lighting. This adaptation effort is especially critical when dealing with RGB images, where no infrared information is available to help the task, and it is undesired when automating the whole weeding process. Our approach provides a step forward towards its elimination by combining a self-designed fully convolutional neural network for semantic segmentation with additional task-relevant background knowledge. This allows us to integrate domain expertise in the form of input image representations, which we learned through tackling this very problem in the pre-deep learning days. These representations include different color spaces, gradients, edges, and several widely used RGB vegetation indices that are all fed into the CNN as a 14-dimensional input, along with the RGB information. These extra representations help us obtain the same state-of-the-art performance as other methods relying on pre-segmentation and expensive NIR cues. This also allows us to make the underlying network architecture more lightweight than those used previously, with around 25,000 parameters, compared to tens or even hundreds of millions. This results in a fully convolutional network architecture that can be trained end-to-end with a smaller amount of expensive label data, and it is lightweight enough to run at the frame rate of a commercial camera mounted on the robot. Thank you very much for your attention.